And now the author shifts to exogenic processes, and that's pretty much what we're going to be on for the entire rest of the semester, along with some things that we're adding in, like the Geomorphology of Ohio, and so forth. So we are on Chapter 7 right now. We are on calendar with where we wanted to be from the syllabus. So let's go ahead and get into the material. Oops, that's not what I wanted to do. Okay. So, Amber, can you give me a wave? Do you see that? Fine. Okay, thank you. So, in this chapter, we are going to be looking specifically at weathering processes and some landforms that are directly associated with weathering. And the way that he's broken this up is a little bit awkward because it's an awkward topic in terms of actually drawing a boundary, for example, between weathering and transport. But I think it works out all right. And the chapters beyond this sort of look at special situations of weathering, erosion, and transport, whereas in this chapter we look at sort of the general processes that are going on. And so, for our purposes, weathering is the breakdown of rocks by either mechanical or chemical decomposition. And as you probably learned in physical geology, many rocks are formed, all rocks basically are formed at temperatures and pressures which are different from that at the Earth's surface. And therefore, they tend not to be in equilibrium with the conditions at the Earth's surface, and that's why weathering of the various types occurs. And so let's think about first what these weathering processes are and sort of what is the outcome from them. Let's start with the outcome, which is weathering debris, and those are things that that come from the weathering process when it's applied to rocks and minerals. And that mainly consists of solids, which are the typical things like clay, silt, sand, and boulders, and so forth. And secondarily, it consists of solutes, dissolved material that's been changed primarily into an ionic state, but certainly into an atomic state, and is not really considered to be a solid anymore. So we have our solutes, which are dissolved matter, and then our solids. Beyond that, he mentions in the book that there's also colloids. And these are sort of intermediate size components, which can be in a semi-solid form, but typically not in a crystalline form. And things like that are gibbsite and boehmite, which are aluminum hydroxides, hematite and goethite, those sorts of things. So really there's three states of weathering debris or weathering output that we are concerned with, which can then be moved away. We'll talk a little bit more about that when we get into our discussion on soils. So let's turn now to thinking about the first and simplest type of weathering, which is mechanical weathering. And it turns out that there are many different ways that can occur, and 4 of them are listed here: unloading, frost, thermal changes or heating and cooling, and then wetting and drying. So first of all, when we talk about mechanical weathering, we're talking about breaking apart of the material or reducing its size. And so I like to think of this as a rock hammer. If we had a piece of granite, we could leave it sitting out on our lawn and let the rain fall on it and dissolve it away and so forth, which would be a very slow process. Or we could take a sledgehammer, a rock hammer, we could hit it and we could break it. And mechanical weathering, of course, is extremely important in the process because every time you break material into smaller bits, you create larger surface area that can be exposed to chemical weathering. And so in concert, mechanical weathering and chemical weathering have a sort of synergy where one can assist the other. So the first type we're going to talk about here is unloading. And if we think about rocks being formed at some great depth, typically some kilometers of depth, and then they go through uplift and they're brought to the surface, they are now sort of depressurized, and so unloading can actually create fractures and break the rock apart as we get the expansion of the rocks due to this unloading. We'll look at some pictures of this in a minute. This also occurs in mines. When we have a deep mine, remember the rock all around us is under intense pressure, but when we sink a mine shaft into that has it's an atmospheric pressure, and so we have a disequilibrium. And one of the dangers of deep mining is something called rock bursts, where the rock basically explodes into the void, and many miners have been killed by this sort of unloading feature. But the more common one is related to exhumation, or the exposure of rocks that were buried very deeply. And so, for example, probably the most famous exfoliation dome in the world is Half Dome here in Yosemite Valley, California, which is on the right, and has a sheer vertical face that we see, which was carved by glacial activity and then subsequent rockfall. But on the back side, on the right, is an exfoliation dome, and we don't at this scale see the sheeting fractures that are associated with that. But if we zoom in closer, we do see those. So this is a view from the other direction, and we are looking at the final climb up to the top of Half Dome. You can actually hike up there, and it's a really cool hike. I did it about 7 years ago. It's a full day hike to get up there. I think it's a 14-mile round trip, and maybe you gain about 3,000 feet of elevation. But the last bit of it is going up these cables, which they've installed in the side, and you can see the people for scale here going up the last bit. But what we're interested in is we can also see the sheeting fractures where this dome structure is exfoliating and large blocks are peeling off, kind of like if you've ever peeled an onion and it has those layers. And this has given it its name and classic shape. It's called Half Dome. So in addition to unloading, frost action, which is when water within a solid freezes and expands, is a important generator of small grains and even large boulders. Freeze-thaw cycles are common in temperate regions, and this type of fracturing is very important, and it can occur, of course, even with things like the unloading. You could certainly imagine if you had an unloading fracture and then water got into it and froze, it would actually even further disrupt the material. Beyond the actual action of frost, the simple heating and cooling of Earth materials actually can weaken them. And there was a very interesting study which was done, I think, published about a year ago by a scientist from North Carolina who actually studied two boulders in different parts of the United States, and she instrumented them with very detailed thermometers and little seismometers to hear cracking noises and things like that. And she was able to quantify some of the things that were going on with heating and cooling stresses on these two boulders, which were in different settings. Wetting and drying can be an important process, particularly if we have clay minerals that are present. Some clays, when they become moistened, will swell, and they can exert a very strong pressure on the surrounding materials. In some instances, wetting and drying leads to the actual disaggregation of the material. That's a process called slaking, S-L-A-K-I-N-G. And that can actually be extremely important in the construction industry, because if you use certain, for example, crushed shale as a road bed, and then it gets wet, it may slake and you may lose the support of the underlying material. One final thing, which we hadn't listed here, is mechanical, physical, but he does in your list in your book, is salt crystal growth. And we'll look at some examples of those sorts of weathering landforms in a little bit. But basically, imagine a porous sandstone through which water is percolating. And when the water gets to the surface of the sandstone, when it seeps out, that water evaporates, and that causes the crystallization of salt right at that interface. The force of crystallization is actually a really strong one, and when that salt precipitates, it may actually wedge apart sand grains, and that process of salt crystal growth can be a very important process in certain settings. Questions about mechanical weathering? So let's move on then to chemical weathering. And there are at least 6 main ways that chemical weathering can occur. And the first is listed there, which is dissolution. He refers to it in the book as solution, but that is not proper usage. Actually, dissolution is the reaction. And in a dissolution reaction, which is probably the simplest type of reaction we think about in geosciences, we are taking material, exposing it to water, and it is going into its ionic state. So an example for this might be salt. If we take sodium chloride, or halite as a mineralogist would call it, and put it into water, it will dissolve very readily. And of course, there are limits to that. If we keep putting more and more solid salt into water, we'll get to a point where we reach the solubility limit and no more salt will dissolve. And in fact, minerals vary in their solubility. The most soluble natural minerals are halite or potassium chloride. So we only find these exposed in places that are dry, because if it was wet, they would just be completely dissolved away. Gypsum is another very soluble material. It can dissolve, over human life scales. Quartz, which is a very common mineral, has a very low solubility, but there are conditions of high water flux or high temperature that can lead it to be substantially dissolved. Our second chemical mechanism is hydration, and this occurs when minerals absorb water molecules into their crystal lattices or at the edges of their structures. And probably the most familiar example we have is if we take the mineral anhydrite, anhydrite, which is calcium sulfate, and we add water to it, we form the mineral gypsum, which is calcium sulfate dot 2H2O. So it's taken the water into the structure. That causes an increase in volume because it's got this water absorbed now, and that actually can drive mechanical weathering as it sort of wedges apart beds and so forth. Our third type of chemical reaction is redox or oxidation reduction. And of course, this is when we have an atom or an ion changing the number of electrons it has. So if it loses an electron, in other words, becomes more positive in charge, that's called oxidation. And if it does the opposite, that's called reduction. When we have oxidation weathering, it's typically where we have minerals containing iron, but it also affects manganese, sulfur, and titanium-bearing minerals, which are, of course, these have to be polyvalent minerals so that they can change their electron state. And in the book, they give an example of one of those reduction reactions. There is, if you've taken any courses with Dr. Senko, you know that bacteria can actually be very much involved in this type of reaction in aiding the reduction or the oxidation. Our fourth type of chemical weathering is carbonation, and that involves the formation of carbonates or the destruction of carbonates. And these are related to carbonic acid, H2CO3, which can exist in various forms in natural waters depending upon what the pH is. But carbonic acid is a very important natural component of water. When we get to our section on karst, we'll talk about that. But essentially, if you take carbon dioxide from the soil and let water percolate through it, you create carbonic acid, which promotes the dissolution of limestone and dolomite. Our fifth class of reactions is hydrolysis. And this one you definitely should put a star by. This is the main process of chemical weathering, and it can greatly affect the decomposition of a lot of important minerals. When we are undergoing hydrolysis, we're taking water and splitting it into hydrogen, H+, and hydroxyl ions, OH-. And those can react with silicate rocks, silicate minerals, either in rocks or in soils, and it involves a swap of the metal ion and the silicate minerals. And that's illustrated on the right here, which is a extremely important weathering mechanism. And you should know this chemical equation. This is the conversion of orthoclase, which is a feldspar mineral, with slightly acidic water to create kaolinite, which is a clay. And that also releases silicic acid, H4SiO4, and 2 potassium ions. The reason why this is important is because this is the basis for converting many igneous rocks, for example, granite, into clays, which make soil. And we don't eat dinner if there's no soil around. Okay? If you don't have soil to grow the grass, to have the cattle graze on it, and so forth, the whole entire food web is disrupted. So this is an example of a hydrolysis reaction, and there's many others which are listed in your book. You can read those over. Our final chemical reaction is chelation. So it's spelled like chi, but it's pronounced chelation. And this is the removal or the plucking off of metal ions by organic acids that come in contact with them. And so in the soil, there are fulvic and humic acids, which form these organic matter metal complexes when they get into contact with metal ions that are present in minerals. Questions about these chemical processes? Okay, so then just briefly, because it's not really a focus of this course, but biological weathering. In certain settings, well, let's back up. If you were to consider humans to be a part of biological weathering, then obviously that would be a huge and widespread erosive force. And we are going to talk about that a little bit later, but for here, we're talking about biological things which are not related to humans. So first of all, if you have plant roots, especially trees that grow into joints or bedding planes, they can actually exert pressure, which can break off rocks and lead to rock fracture. There are effects from lichen, which can corrode the rock from their biological processes and also leave a dark spot, which absorbs more thermal heat, and so encourage thermal weathering. There's lots of these sorts of small things. In marine settings, we can have boring organisms, some of which are really good rock destroyers. And there can also be bacteria, algae, and fungi, which go into rocks. And in some settings, biological rock erosion is really extreme, and you barely, you have a bedrock shore, and it's nothing but jagged spikes because of all the erosion that's going on there. All right, so let's look at a couple more pictures. I didn't splice these in, but so here's an example of some clays. And clay mineralogy is an extensive and complicated topic, but basically there are three main structures of clay types: the kaolinitic clays, the illitic clays, and the smectitic clays, and they are based upon what their layer structure is. So the kaolinitic clays have this one-to-one layer with a thickness, typical thickness given there in angstroms. So it's a tetrahedral organized sheet bonded to an octahedral sheet, and then it just stacks on similarly. Illite's a bit different. You've got these two tetrahedral sheets that are facing each other, and they're facing inward, you can think of it as. And then finally, the smectites have those same type of structure as the illite, but in between them, they have an additional layer which bonds the two of them together. pH can be a big control on how chemical weathering proceeds, and this chart from your book just gives some pH ranges of common things. Of course, alkaline pHs are those that have a value of over 7, and acidic pHs have a value lower than 7. And some common things are listed there, tomato juice, battery acid, and so forth. But what we're more interested in is natural things, like we identify that seawater has a pH that's alkaline and it can be close to 9. Acid rain is anything where the pH is below 5.6. In some cases in the northeast of the United States, pH might be closer to 4. And remember, of course, the pH scale is a logarithmic scale. So as you go from pH 6 to 5, you're becoming 10 times more acidic. Okay, I want to turn now to the second main part of this chapter, which is the weathering products. And so these are the things that are coming off, in particular, the solids. We know certainly that there are solutes that are being carried off by rivers and into the ocean and so forth, but what we're concerned with here are the solid products. And so let's first introduce two terms. The first is regolith, or sometimes pronounced regolith. And in the book, he describes this as the weathered mantle, which is all weathered material lying above the unaltered or fresh bedrock. And this is a pretty broad definition. I actually prefer the original definition, which is any loose natural material at the surface of the earth. Any loose natural material at the surface of the earth. So that definition includes such things as glacial till, glacial outwash, alluvium, soils, sand dunes, gravel bars in a river. Okay, it's anything that's loose material and it's at or near the surface of the earth. That includes all soils, right? Because soils are relatively loose material. So soil is a subset of regolith. And if we think about the process that goes on when we make soil or make regolith, it is a time-dependent process. So if we're in Hawaii and we have had a recent lava flow and it has cooled off, when we walk out there, what we see is bare rock. Okay, it's got no soil on it. But if we come back, maybe even 10 years later, we start to see some vegetation. We start to see some soils forming, some thin soils, from the weathering of that basalt, and also because dust is getting blown in and maybe accumulated on there. So these are processes that go on through time. And if you think about, let's take an example of a granite. This is what a typical weathering profile looks like. So let's start way down at the bottom where we have fresh bedrock, and we see that it is granite and it has two quartz veins, well, one quartz grain down at the bottom going up from it, which is that light tan. And even fresh bedrock has some fractures in it probably, and those are illustrated there. And if we go upwards from there, we get into an area where there's some weathering has occurred, and we can still see parts of the relatively unweathered granite as what are called core stones, which at this point are angular. And then around that, we see grus, which is weathered granite. And I meant to bring some to show you, but I will try to remember to do that next time. But basically, it's just weathered granitic material. And we call that zone the sap rock zone. And that's the beginning of our regolith. As we go up from there, our core stones become smaller and they become rounded, and that's the beginning of the saprolite zone, still in the regolith. And as we go farther and farther up, we finally get into the mobile zone, where basically the core stones are no longer really present. There may be some residue of them, which we see. Let me get my annotation on here. Up in here. And we also see something interesting. This is why this is called the mobile zone, right? We've got a slope that's sloping down this way, and so there's gravitational processes that are coming into play now. And so, for example, this quartz vein, which normally would have gone up like this, is sort of stretched out along here because we get more downhill movement the farther we are up in the slope, and less movement here. The arrows are shorter. We'll talk more about that as we go on, but in both of these instances, we see this sort of bending downhill as the material is transported. Oh, let's see. So what else do we have as this material is broken up? We can create talus or scree, and we'll show some photographs of those in a little bit. That's just material that is accumulated down at the bottom of a slope. It's being transported under the force of gravity, and similar sorts of things. Duracrusts and hard pans are another type of weathering product, and these come in a variety of names and types. A duracrust occurs when we have dissolved material precipitating within or on top of the weathered mantle. So you can think of this as a form of cementation, of a joint together of the regolith material. And these can be quite important because they can be extremely resistant to weathering and end up capping hills and reducing erosion and so forth. And so some of the types that we see depend upon their mineral content. So ferricrete is an iron-rich duracrust. Calcrete is calcium carbonate rich. Silcrete is silica rich. Alcrete aluminum rich. Gypcrete is gypsum rich. And magnacrete is rich in magnesite. So all these forms in different types of settings, depending upon what the chemistry of the setting is, and can have significant impact on the erodibility of an environment. And we'll look at an illustration of that in a minute. So I want to talk now about soils. And I have to tell you that the treatment that our author gives to soils in the textbook is completely inappropriate and short. Soils are an essential component of geomorphology. And in the entire book, he has less than a page talking about soils. And I don't know why that is, but that's a real failing of the book. And so in our lecture today, I've added in some other materials regarding soils so that you can be aware of them at least a little bit more. So if you wanted a definition of a rock, you should go to a geologist to get it. And I would say you should do the same for a soil. In the book, he doesn't really define soil, but the soil scientists, or pedologists as they're called, do. And in a brief definition, they would say soil is the portion of the regolith that supports plant life and where soil forming processes dominate. But let's use the formal definition that the Soil Science Society of America says. So there's two definitions. The first is the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of land plants. Their second definition is a little bit longer and is a little bit more genetically related, genetically based. So the unconsolidated mineral or organic matter on the surface of the earth that has been subjected to and shows effects of genetic and environmental factors of climate, microorganisms, conditioned by relief, meaning it can vary depending upon what the local relief is, acting on parent material over a period of time. As a product, soil differs from the material from which it is derived in many properties listed here. So this is really what differentiates soil from regolith. If we are sitting on a sand dune having our picnic lunch, are we sitting on soil? What do you think, Brooke? Oh, maybe Brooke's not with us. How about Josh? What do you think? Is it soil the sand dune we're sitting on?
A sand dune, you said?
Yes, a sand dune.
Probably say it's probably a solid mineral, right?
Sorry, you're breaking up terribly.
Can you hear me now?
Sort of. A soil or not?
I'd say yes, since it's like a quartz, right? So it's
It
like
is.
an unconsolidated mineral quartz.
It is a mineral and it's unconsolidated. So how does a sand dune get where it is?
By wind.
Yeah, so wind deposited it there, and according to our definition of a soil, what else has to happen to the material after the wind blows it there?
Oh, it has to serve a medium for growth of land plants, right? And
Yeah, or
nothing can necessarily grow on a sand dune.
Yeah, most things can't, but the real factor is with the bottom part of the definition. It hasn't changed. It hasn't been weathered. It hasn't been converted chemically. It's just sitting there. It's just a pile of sand. And so in that case, we would be having our picnic on regolith, but we wouldn't be having our picnic on soil. So the idea is that it has to have a change. All right, thanks. So soil typically forms in horizons or layers which have different characteristics, and you are responsible for knowing this diagram, and you will be asked to create it on a quiz or a test. The typical sequence is given here, OAEBCR. OAEBCR from top to bottom. And so all of these horizons may be present for every soil. This is the typical horizon that we might find, for example, in the woodlands of the eastern United States. So the O horizon at the top is, O stands for organic matter. We would also call this humus, H-U-M-U-S, okay, which is different than hummus, H-U-M-M-U-S, which is the tasty Mediterranean dip that we have with pita. Below that is the A horizon, which is commonly referred to as the topsoil. And this has humus in it. It's also got living things. It's got minerals. It's sort of a mix of these different mineral and organic materials, and that's the soil which is best for growing things in. Below that is the eluviated horizon, and that's also called the zone of leaching. Well, the way that soils form is that water percolates down through them. And so you can sort of think about it like if you're making coffee and you're pouring hot water through the grounds, and that flow of water is leaching out or carrying away things from the coffee grounds. And in the E horizon, we are leaching or pulling material outward and moving them down. Below that, we get into the B horizon, which is called the subsoil. And there we are accumulating the things that have been leached out from the A and E horizons. So we're sort of moving things down and reprecipitating or redepositing them in this lower soil. Below that, C horizon is weathered parent material. So it's partially broken down minerals, and it's not solid bedrock. And then finally, the R horizon is the bedrock that's underneath. My wife is a soil scientist, and one day I asked her, how do you know when you're at the R horizon? And she said, you can't dig anymore with your shovel. That's the way that they separate it out. Questions about these horizons? All right, let us leave our discussion of soils and just look at a couple examples of some of the things that we talked about earlier in this section. So this is plate 7.3 from your book. This shows some scree slopes, which are these rubble which is accumulated at the base of a cliff. If you've ever walked up to a cliff, you've probably have struggled, to get through this stuff because it's loose and you keep sliding back until you get to the base of the cliff. So that's a landform that's associated with this. If we have loose material that has come out of sort of a canyon or a gully like this, it frequently forms this cone shape. This is called a talus cone. And now let's use that as a shift into our weathering products or landforms that come from these weathering processes in the few minutes that we have left. So these landforms which tend to be not on the huge scale, like not mountain chains typically, are a result of their underlying, their underlying structure, what material they are, the processes that are acting on them, and how much time has elapsed. And so in the book, he breaks these into three different sort of groups that based upon what's dominantly going on. So the cliffs and pillars, rock basins, and then joints and weathering on the broader scale. And so cliffs and pillars tend to form in conglomerates, limestones, and sandstones. And we're really lucky here in northeastern Ohio to have some great examples, like in the metro parks, up in any of the areas we call ledges, whips ledges, and so forth, have these type of structures, and we'll learn more about those on our field trips coming up. In dry lands, they take some strange forms, which we'll look at in a minute here. Rock basins, or llamas, are these bowl-shaped depressions that typically form in more porous rock, but sometimes in limestones or even in granite, we can get them. These sort of dissolution forms can occur either due to the action of running water, or sometimes the action of wind, or sometimes that crystal weathering that we talked about beforehand. And then finally, just overall joints and weathering, sometimes due to differential type of differential rock types, we can create these sort of isolated mountains called Inselbergs, island mountains in German. And depending upon their shape, they could be called Bornhardts, Nubbins, or Castle Copies. Well, this is one that I meant to show earlier. Sorry about this. This got out of sequence. Look at this in your book. This talks about how a duracrust can lead to an inverted topography where what was a valley now becomes the top. Here's an example of the process where we are weathering jointed rocks, and we've got two stages here. First, we're weathering down below the land surface, but then we're removing the material that's in between. Whoops. And we're left with these piles of boulders. This is an example of weathering pits. These are rock basin examples. Hard to see, it's a little bit fuzzy, but there's a person in here for scale. This is a tuffani that is formed in a granite boulder, okay, a weathering pit. These are typically related to salt fracturing, as we discussed before. This honeycomb weathering, which is a little bit small, there's a lot of examples of this in the metro parks in Summit County. This particular one is a coastal example from Oregon. The joints can come into play directly. This is Devil's Postpile National Monument in California. And so we get the talus that forms at the bottom there, and then the vertical cliff face. This is an example of a pointed dome. This is a granite Bornhardt in Namibia. They're not always pointed. Here's an example from Brazil where differential weathering has caused these residual mounds to be left. A little bit smaller example, person there on the left. This would be called a tor. It's made out of granite. And I think we're about a minute over, so we're going to cut it there. We're most of the way through the chapter, so we'll finish it up on Wednesday. Are there any